Howdy. Are you guys going to be able to hear me if I just project, or do I need the microphone? Okay. Is this better? Okay. What about that? Everyone can hear me? You're the furthest away, so I'm going to take your thumbs up as a good sign. Okay. Welcome to the review session. If you have not been to my office hours before, how my office hours usually work is I just take questions from y'all. And it can be about homework or about concepts. I've already gotten one question of just making like a general list of what to study for the exams or this exam. It will look a lot like your homeworks, like a lot like your homeworks. So make sure that you know all of the like labeling things that we do. So being able to add hydrogens and knowing your stereochemistry, I'll write this down. So some other ones that I'm adding up here are identifying lone pairs, being able to figure out identical atoms. So if you have two of the same structure and one is in 2D and one is in 3D, or one is turned 90 degrees, or one is a mirror image, can you locate the identical atoms and number it like we've seen in, I think, all three homeworks? Then differences, can you compare two structures? I think we just had a question like that in homework 3. And then acid-base chemistry. And so the acid-base chemistry, that's going to be, can you identify your acidic protons? Can you draw the conjugate base? The pKa table is going to be really important because acid-base chemistry leads us into buffers. So you need to know what a buffer is, and then the two equations that go with buffers, which is your Henderson-Hasselbalch equation, and then your proton concentration equation. And then, of course, chirality and identifying enantiomers. You have had homework assignments covering all of these questions. The homework questions that talk about these subjects are very similar to how the exam will look covering these questions, because there's really only so many ways that you can ask about these topics. Yes, no, maybe so. Lots of thumbs up. Okay. Are there specific questions about this stuff? Or do you want me to just like review? I know we haven't had anyone go over problem set 3. You just have the key. So if you want, we can start there. Or what's up? Yeah. This is the Henderson-Hasselbalch equation. He will give you this equation. And then this is the other one that you should know. Where this is the concentration of protons. That one he doesn't usually give you. So you should know it. But those are the only two equations you should know. Yeah. So wait. You should know resonance structures. Specifically, how they relate to acidity. Yeah. Electron dense areas are any places where a negative charge lands when you're doing resonance structures. Electron deficient atoms are any place a positive charge ends up when you're doing resonance structures. Yeah. So electron rich is anywhere a negative charge ends up during resonance. And electron deficient is the same, but with positive charges. Also, if anything is unclear up there, just let me know and I can rewrite it neater or zoom in or make it a different color. Yeah. What question is it? So the reason that is, I'll write out the equation. That's because what he does is he subtracts the pKa from both sides. And because you're dealing with a buffer where the pKa is like what you base your pH off of, they even out. And that's how you get from that to 0 equals log of base over acid. What's up? So question 8. How many people want me to just go over problem set 3? Like in its entirety? Okay, close. I'll just do that and we'll get to question 8. Let me download a blank problem set. Okay, so this first question, you had to look on the internet for this stuff. There will not be a question like this where it's expecting you to have any kind of structure memorized on this exam, but a lot of these questions where he's looking for you to look something up, it's more to familiarize you with all of the online resources that you can use as a scientist. So we're flexing those muscles while also learning about stuff that has to do with what we're talking about in lecture. So the structure of heat is this. And our conjugate acid and base, or the acid itself and the conjugate base, we are going to have a protonated amine as our acid, and the pKa of that is 7.48. And then our base is missing that proton. So that answers B and C. And then our useful buffering range is 6.8 to 8.2, which is around plus or minus 1 from our pKa. What's up?
Why is it plus one nitrogen? Could it be on the other nitrogen?
It chemically could be on the other nitrogen, but this nitrogen is closer to that sulfoxide group, which is why it pulls more that way than to the other nitrogen. Other questions on this one? Okay. Question 2. We kind of got into this one a little bit already, But this one, we're gonna use that Henderson-Hasselbalch equation, which is the pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. So, because we're dealing with a buffer, the pH and the pKa are about the same. So we can do this. Or if you wanted to plug it in, you could plug in the values. We know our concentration, so we can plug that in. How do we take the opposite of a log? To the 10 to the power. So 10 to the power of 0, what does that equal? 1. We multiply both sides by x, which is our acid. So we have 1x equals 1. And then we need to use our molecular weight to change this molarity into grams. Because this x is our acid, which means its unit is moles, or molarity. Our molecular weight is 94.1 daltons, which I think he has a typo in the answer of 91.4. I think it should be 94.1 grams, because you would divide both sides by 1. What's up?
How did you know to put the 1 into the base of the acid? Like, where did you get like the 1 from?
So the 1 is from our molarity here. You can't see what I'm doing. Our molarity here. And this part is nitric acid. So this is our acid. We're looking for how many moles of the acid. The other part is the conjugate base. What's up?
All fun for questions.
If he gives you both and they're different, use those values. If he doesn't, you can assume they're the same. What's up? Mhm. What's up?
So, pH values, how do we get differences for pH?
Because buffers work in their specific pH range that is calculated based on their pKa, we're operating under that assumption right now.
So unless specified otherwise,
Yeah.
we're gonna continue.
Yes.
Okay.
What's up? The exam does not have a periodic table on it. I don't think you need it. You will have the pKa table though. If you do need it, the proctors will put it up on the screen. What's up? 94.1 is the molecular weight of this molecule. You would add it up. So you would need the periodic table for this question. You would need the periodic table. If you need it, they will provide it. Same with the pKa table. But I'm trying to think about the exam. I'm pretty sure you don't need it. What's up? I simplified this. So I multiplied in this, I renamed acid as X. You multiply both sides by X, which evens out on this side, and so you have 1x equals 1. Other questions on this one? Yeah. So this is the molecular weight of what we're looking for. So this equation only gets us as far as molarity. And then we know we are making 1 liter of it. So then we go to grams using the molecular weight, which Dalton can also be grams per mole. Other questions? Yeah. I can't hear you. Enantiomers have nothing to do with this question, but we will talk about them. What's up? Yes, in grams. Other questions? Okay, well, yeah. I didn't. I took it from the problem. With the buffer, yeah. Unless they're given to you differently. Yes. Other questions? Yeah. So 94.1 is the molecular weight of this molecule. So you can either plug it in, like plug that formula into a molecular weight calculator, or you can do it by hand using a periodic table. And then you have to use grams per mole to do the unit conversion. Okay. Good to move to question 3 or no? Yeah. Good? Okay. So, which of the buffers shown on lecture 6, slide 13, would you use to buffer a solution at pH 8.2? How would you start this question? Yeah. Yeah, that's a pretty good place to start. How do you determine which of these would be good at buffering a solution that's at pH 8.2? Yeah, if 8.2 is in their range, they can work. So there's 10 that he gives you that would work for this. I'll just write them out. Which would have the best buffering capacity at 8.2? Why would this one have the best? Because its pK is 8.25. Lysine is a close second at 8.26. What's up? There won't be a question like this. He'll give you like the structure if necessary and the pKa if necessary. Or it will have enough similarity to something on your pKa table. What is the pH of 100 millimolar solution of nitric acid? Nitric acid is strong acid. Where would you start with? Oh, question. Yeah.
So is the range one, like, I for mine starting with like trace, I didn't get like the four before this, so is the range like one pK?
The range is on that table, and the other ones also include 8.2. Some of them, their upper limit is exactly 8.2. And so that might be why you excluded them. But if it's still included in the range, it will work. Other questions on 3? Okay. Question 4. Where do I start with this one? What equation should I use? What can I plug in where? 100 millimole is equal to 0.1 moles. So we can say pH equals negative log of 0.1, and our pH equals 1. Questions on this one? Yeah.
So I know like you plug it into that, but this is the strong acid. So how would you do it if it was like not strong acid?
He won't ask about that. If you really want to know though, you'll use the Henderson-Hassel multiplication. Questions about this one? This one is pretty straightforward. And if you struggle with this one, I would review it because there will be a very similar question on the exam. What's up? Oh yeah, he's not grading them. I am. Also, if you have regrade requests, I process those. So submit them if you feel you've been wrongly graded. What's up?
So those three carbon like H3, because he's done that to some extent. Which is right, like all I.
These ones? As long as you indicate in some way that there are 3 hydrogens, I will give you full credit. Other questions on this one? This type of question will probably be on every exam that you have. Please let these be easy points for y'all. Please. Carbons should have 4 things. They have four spaces. Everything should have a perfect octet. Please, please, please don't get points off on this question, okay? Now, this question. We'll start with this. Any thoughts, hypotheses, guesses? Planar. Why? What's up? No lone pairs, and it's got 1, 2, 3 things attached. Okay, what about this one? How many things are attached to it? Does it have any lone pairs? No. So this one is also trigonal planar. Read the questions fully. So, what about this one? Tetrahedral. I'm saving the hardest one for last. What's this one? Also tetrahedral. Now, this dear sweet nitrogen. How many people think pyramidal? How many people think planar? Okay, so this one has to do with resonance because our little electrons here can turn this into a double bond and push electrons onto the oxygen, where we will then have a double bond there. So this one is also trigonal planar. What's up? If there is a double bonded oxygen as a neighbor, yes. What's up? This would not be a chiral center because nitrogens can only be chiral centers when they are in a ring. In a ring. Like if it's in a cycle, basically the deal with nitrogens is they have resonance like this sometimes. If it has resonance like this, it can't be chiral because it means that half the time it doesn't have 4 substituents. Now, when it's in a ring, that conformation is locked. So it means that even if there is a lone pair, that lone pair can't move around. So for nitrogens, they can be chiral with a lone pair if they're in a ring. What's up? No. Yeah. What's up? If it was a carbon, it would be trigonal pyramidal. What's up? No, because of resonance. Other questions on this one? Yeah. That one would be, yes. Because it has the double bond next to it. Mhm. It's because it has resonance with that double bond where the electrons are kind of always moving. So it looks more like 1.5 bonds between both of them rather than one with a double bond and one with a single bond. Yeah. It's really only nitrogen in y'all's case. We aren't going to work with metals, so you don't have to worry about those. Other questions? Yeah. Yes. Other questions? Yeah. Because it's for the same reason. This double bond has resonance, and so it doesn't have 4 unique substituents because sometimes it has a double bond here. It is in a ring, but this takes precedence. Other questions on this one? I'm going to move on. Draw the lone pairs associated with the atoms marked with an arrow. This one should also be 3 points if you see it on an exam. Please don't let me mark off any points for a question about lone pairs. Please, please, please. How many lone pairs should the sulfur have? 4 lone pairs or 4 electrons? Okay, what about the nitrogen? 1 lone pair. What about the oxygen? 2. Any questions on this one? In all, yeah. 1, 2, 3, 4, 8 lone pairs, or there's 5 here. 8 electron. Yes, the octet. Yes. Yeah. What's up? Love that you guys are hopefully talking about chemistry with each other, but would like to hear the question over here. What's up? No. Other questions on this one? Again, if this kind of question is on an exam, please get all the points. The exams only get harder. This is going to be full of gimme points. Please, guys. Okay. Penicillin has 3 chiral centers. Identify each with an arrow. Anybody feel confident on their 3 identified chiral centers? And want to come up here and circle them on the iPad? I believe in you guys. We have a winner. There you go. What are the rules for a chiral center? 4 unique substituents. Questions on this problem? Yeah.
Why wasn't the one on the head, just like the sulfur?
This one?
Why would that?
Because these are both CH3s, so they are not unique. Because you have 2 of the same thing.
I thought you said every carbon, like whenever.
That was a blanket statement that is not true. What he means is, like with this one, this is a carbon. Let me use a different color. This is a carbon, and it is attached to 2 carbons. But those 2 carbons are unique. They're not the same carbon because they have electronegativity and like electron trading with their partners. And so this carbon has reactivity with this oxygen and with this nitrogen, whereas this one can talk to the nitrogen and the sulfur, and so they're different. What's up? Yeah. That one that you've drawn would not be chiral because it's symmetric. So both the carbons would be the same.
And it's like that, like I feel like it's a dog.
Yeah. Yes. What's up? No. Other questions? Yeah. This one? So this is attached to 1 COOH, 1 like carbon chain, 1 nitrogen, and then it has an implied hydrogen. So those are the 4 different things. Other questions? Moving on. Do I need to cover this one? Okay, cool, because it's kind of time intensive. And what about this one? Question. It's okay. You don't have to. For the most part, the hydrogens, you won't have to number in general. Like if you just number the main body, that will be fine. Yes. Other questions? Okay. Use estimated pKa values to determine which of the following reactions are thermodynamically favorable. What is the first step with this kind of question? Identify your functional groups and find their pKa's. So in this first one, in A, on the left-hand side, what is our acidic proton? The one that's drawn. What about on the other side? Also the one that's drawn. What are their pKa's? What is the pKa of an alcohol? 16. What is the pKa of a carboxylic acid? 4.8. So which direction would this go? The opposite of what is drawn. So it would go this way. Which, hey, would you look at that? Is the option for the next one. So C, what functional group is this? Is it just an alcohol? Is it just an alcohol? Yes, no? It is not. It's a phenol. What is the pKa of a phenol? 10. What is this? Any takers? It is an amine. What kind of amine? It is a protonated amine. What is the pKa of a protonated amine? 10.6. What is the difference between our two pKa's? 0.6. So, what direction is thermodynamically favorable? The way it's drawn, yes. Any other options? Yes, both of them work because the difference is not very large. What's up? I would say, I think 3 is what his cutoff is. What's up?
So would the correct answer technically only be since it doesn't give us the option for equilibrium? Or is it B, C, and E?
It's B, C, and D. Because it's thermodynamically favorable in either way, you don't have to draw it together. It just means that both work. So you could draw it with like a double arrow like that to save space, but that's not what he was testing you on. Other questions on this one? If the difference is under 3, it will be in equilibrium. Other questions on this one? Okay, moving on. Indicate the 4 differences between structure A and B. Who feels like they can confidently find at least one of these differences and wants to come do it on the iPad? No one? Yes? Are you gonna do one or more than one?
I could do two.
Go crazy.
Oh, wait, these highlighted or, oh shoot.
Whatever you would like to do.
Okay, I was gonna highlight it. I like color. And then this one.
Okay, you wanna indicate them on the A as well?
Oh, yes. So was this one. Okay. Nope. Skew.
Mhm.
Yeah. Okay.
Anybody know what the other two are?
Not too complicated.
Yes.
Perfect. That was really embarrassing. Wait, am I doing this right? Thank you. And that corresponds to this one.
Excellent. Those are our 4 differences. Do you have questions on? Yeah.
Where does this reason reflect circular differences?
Yeah, that's fine. What's up? Yes. What's up?
It's not a follow-up to that. Like on mine, I have the same ones, but I labeled like 1 on this one and 3 on the other. Do you want us to put like 1, 1, 2, 2, 3, 3?
It doesn't matter.
Oh, so as long as it's like,
As long as it's legible,
okay,
you'll at least get some kind of partial credit. What's up? Can you speak a little bit louder? Mm-hmm. Yes. Yeah. Although usually on exams, he doesn't tell you how many to look for in these kind of questions. So like earlier, it was, you know, there's 3 chiral centers on this. There's 4 differences here. On the exams, he usually just says, what are the differences? Or what are the chiral centers? Other questions? Okay. Question 7. How did people feel on this one? Because this is where we're starting to get into new territory. Seeing a lot of thumbs down. Okay. Resonance structures will always start with electrons. So we're going to start with the lone pair on this nitrogen. The basic point of resonance structures is moving electrons around to find where they are most likely found. In this case, we're going to be dealing with negative charges. So what we're identifying are electron-rich places. In the next question, we deal with a carbocation, which is a positive charge, which is a lack of electrons. So we'll be looking at electron-deficient places. First thing we're going to do is move our electrons. These electrons, the only place they can go is onto that carbon. But that would then overload this carbon. So we have to send the electrons from this double bond onto the next carbon. So because we took electrons away from the nitrogen, it's now deficient, so it will have a positive charge. We then formed a double bond here. We took away the double bond that was here and made a negative on this one. Everything else remains untouched, so we can just add it in. We're then going to continue doing that until we hit the end. So we're going to take our electrons, push them down to make a double bond. This carbon is now overloaded. So it will push its electrons onto its neighbor. Our nitrogen is still electron deficient, so it will still have that positive charge. This double bond remains unchanged. We made a new double bond and put electrons onto this carbon. This double bond remains unchanged. We're going to do it again. We're going to take these electrons and make a new pi bond, which forces these electrons onto the next carbon. We're going to do it again. We're going to push these electrons onto this bond, which is going to push electrons onto our oxygen. Now, with this structure, the only place that we could push further electrons is back down, which would just give us the same structure, and we would move backwards down the pathway until we got to our original structure. So this is all of the possible resonance structures for this structure. Yeah. Yes. What do you notice about the overall charge with all of these molecules? It stays the same. This structure, what is the charge of the overall structure? Neutral, 0. It has no positives and no minuses. What about this one? It's also going to be 0 because we have one positive and one negative. That continues to be the case for all of our resonance structures and will always be the case for resonance structures. If you start with a positive charge, your overall charge on every resonance structure should be +1. If you start with a negative charge, all your resonance structures should have an overall charge of -1. Yeah. You could, they would come the same, they would basically just reverse in the same way. Actually, you can't start with the oxygen. It does not have anywhere to go. Because then you would create the cation on the oxygen. If you start like this, you would have to take an electron pair like this, and you would make a triple bond, and that wouldn't work. So, using all of our resonance structures, we can now identify which are electron rich. And it's going to be any carbon or heteroatom that had a negative charge. So, not the highlighter. Our oxygen had one. This carbon had one. This carbon had one. This carbon had one. And our nitrogen always had the lone pair to start. So those are all the electron-rich sites in this molecule. Yeah. Yes, because it's now harboring the electrons from that double bond. Other questions? Yeah. Because it had a lone pair to start. Other questions? Yeah. Because they never had a negative charge in all of our resonance structures. So they're not electron deficient because they never have a positive charge, but they're also not rich because they never had a negative charge. Other questions? Yeah. Nitrogen will almost always be rich. It's almost always a carbon that will be electron deficient. Yeah. It is sometimes a pattern, but I wouldn't use it as a rule of thumb. It's a rule of pattern when you have a conjugated system, which means that you have double bonds every other. Yeah. You would want to draw out all of the structures. Mhm. It would really depend on what else is in the molecule. Yeah. 6. A lot. It's 10 pages. Well, your pKa table is 2 pages and the cover is 1 page. So it's 7 pages. Yeah. All of question 1. No. I like my job. I would not like to lose my job. This is being recorded. No. So I would say question 1 is a lot of the reactions that I was like, these should be gimme points. So the other ones, I would say, are less free for all points. Maybe. Okay. How many questions? 0. But 4 of the 6 questions are multiple parts. Okay. It's like 18 questions when you break up the parts. Some questions I would say are easier than others. You'll have an hour and 10 minutes to do the exam. Yeah. I don't know. Yeah. A 35 out of 150. It's out of 150 points. Yeah. I'll cover question 8 now if people don't have other like housekeeping questions. Yeah. Can you talk a little bit louder? Can you speak up? Okay, other questions on this? If not, I will move on to 8. So, use resonance structures to identify electron deficient sites. We are basically going to do the same thing that we just did, but instead, we're going to fill the gap that is a cation. Cations are positive charges, and it's basically an empty orbital where there can be electrons. So we're going to continually move things to fill the new vacancies that we make. So with this one, we have this cation, and the only bond in distance is this one. So that will be our first step. We can add in all of the things that we didn't change, our new double bond, and our new electron vacancy. We'll then do the same thing. With this one, we have 2 directions we could go. We can pull from our carbon chain like this. Or we can pull from the ring. These are our resonance structures. So now we can go in and identify all of the electron deficient places, which is where there were positive charges. So this was where our original was. Then we had this one. Then we had this one. And then we had this and this. So those are the electron deficient sites. What's up? I don't think I understand your question. You could do it either way. What's up? I do. No. They're on the top of my desk. Is he asking for them?
I asked him at what time he got.
Okay. I do. Okay. That's gonna be your proctor tomorrow, guys. His name is Brian. Okay, what's up? Yeah, it's like playing hot potato with the positive charge, and you just keep tossing electrons and filling the vacancies.
Like the arrows go this way for the galaxy, like that cation.
Yeah. Other questions on this one? What's up? Mm-hmm. I don't think I follow your question. You should have all four drawn because these are different from each other. What? Yeah. So there's not a favorable one. The way that he does it in the key is separating them out so that you only draw like in one chain. I prefer to do it like this, where if there's branch offs, I will like draw them like branch offs instead of how he does it in the key, where it's like one continuous pathway. Either is correct. So they're both filling the same problem, which is they both fill this cation. But there are two neighbors that could fill that. And so either one would work, and we want to know both of them. But there's not really any rule, at least with this, about which one. Other questions? Yeah.
You're not supposed to do purple and green. You're supposed to do both.
You need to have both. I just condense them like that because I have the different colors.
So you can't go from red to purple to green, right? You can't.
You could. So I could go here to here, and that would get me to the green. And for the pink one, I could go here to here, and that would get me there. Yes, no, maybe so. Okay. His doesn't have them drawn out that way, and it might be easier for you to follow on his key if this is the part that's tripping you up. Other questions on this? Okay. So we just did resonance questions. Does anyone feel confident enough to do A or B? Yeah? My drawing is really sloppy. That's okay. I think mine worked out. Sometimes it turns off. Wait, whoops. How do I undo something? Do you want to draw the arrow on this one to show how to do that? Excellent job. Any brave souls feel like attempting B? No? Okay. I'll do it. So with this one, you have two directions you could go. You could go into the ring, or you could go out of the ring. You go out of the ring, you can do this. You go into the ring, you will do this. Are there more resonance structures that I could draw? Yes, because I can keep pushing this around the ring. Between A and B, which one has the most resonance structures? B. So because B has more resonance structures, it will be more acidic. That's because the loss of this proton can be spread out across a lot more structures. Whereas the loss of this proton, there's only two possible forms that it can take. Whereas with B, the loss of that proton, there's a ton of different forms it can take. So it can really delocalize that loss and feel it a little bit less. Yeah. He doesn't give you super, do you guys need the lights on? I can turn them back on. Good? Okay. He's not gonna give you like huge structures where there will be a billion different resonance structures because you only have an hour and 10 minutes.
Yeah.
And he knows that there's a time constraint. So yes, you should write all the resonance structures. They won't be super complicated. Yeah. Yes. It's also a good way to make sure you get some kind of partial credit. If I can see where you were going, it's easier for me to justify giving the points. Other questions? The answer is B. B is more acidic. Okay, moving on. Oh, JK. That's the last question from the homework. Yes. This is also being recorded, so you guys can like rewatch it. My notes?
Yeah.
I do. Okay. If you don't have other questions, you can go. But if you have other questions, I will answer them now. Other problem sets, lectures, what's up?
You have the epi for the heaps.
Mhm.
How do you know the hydrogen doesn't the conjugate acid?
It's something you look up.
I wanted to ask, so for this one, we found the pKa of this one, but why not the proton or the acidic proton like that?
That's the conjugate base.
Oh, because I'm okay. And then
That's
this one, well, this one is the base too, no?
This is the acid and this is the conjugate base. This is the acid and this is the conjugate base. So they're like
Oh,
flip-flopped.
okay, that makes sense. And then this one, okay, I understand how you got the 94.1, but I don't understand why we did this if the answer was 94.1. Because I understand it's from this.
Because the molarity won't always be 1.
Okay,
So you
but in
can't
this
always
case it
assume.
was. Okay, makes sense. Thank you.
What's up?
So on this one, what would happen if, would he ask like if it was like 2 liters? Or
He
like
could.
more than one? What
Yeah.
would we do with that then?
It would, so this final answer is in molarity. So that is where it would factor in because molarity simplifies to moles per liter. So then you
Okay.
can multiply it by 2 for 2 liters.
So then like, if he asked for 2 liters, would this be 2 capital M?
It would still be 1 capital N. But remember that capital M is equal to moles per liter. So then you would have to multiply it by 2.
Okay. And then you do the same steps after.
Yes.
Okay, thank you.
What's up?
I had a question on both problem set. Actually, I didn't understand because I know for this one is that.
Yes. That is a good question. That I think is best answered with this. Do you have a model set?
Yes.
I would make the molecule like this, where you have each one is a different color. And this is what I would bring to the exam. You don't really need to build an entire molecule in the exam, but build one of these, and then on your worksheet for your exam, you can label CH3, CF3. So this would be blue, and this would be green, and this would be red, and this would be black. And then you can have the 3D model in your hand. And so comparing them, I would go this to this. F3C is what's in plane for both of them. So in my case, it's green. So I would hold on to that one and I would turn it until my bromine is in plane. Well, then this is flip-flopped because we want the CH3 to be here and the H to be here. And no matter how much I turn this, it will never be that way. What I would have to do is get a mirror image. And so if you have it, I can't imagine it in 3D. But this helps. This helps to like see it in this. And so then you have this one, or we'll say we have the model. And if I switch this, so this is my CH3 and I bring it into plane, then my bromine and my hydrogen end up in the right place with the wedges and the dashes. So these ones are identical. And then you can try it again with these ones and they're identical. But A to B or A to C or A to D, you always need to take the mirror image. It would never turn to end up as the same.
And black means it's coming off, and then the wedge means it's stuff.
So let me make sure I'm right before I. Wedges are always towards you. Dashes are always into the page.
Okay, thank you.
What's that?
How do I get to the room with the testing accommodations? I couldn't figure out.
It's in this building.
Yes.
So you will come into this building, take the elevator or the stairs up to the third floor.
Is the elevator?
It's right, there's one on either side of the building. So there's one that's right out here. If you come in through either of these doors, there's also one at the end of the hall. If you come in over there.
I'll just come in there and figure it out. And are we allowed to use like colors? Like if I have like.
Sure. What's up?
I got lost towards it. Hold on, let me get there. So this part.
Yeah.
So with all moving around, what about this part right here?
What do you mean?
Okay, like okay, so let's say this one goes here, right? And
That one could never jump that far. It has to jump to the next one. So that one would have to jump to this bond here, not all the way over here.
so this one goes here. That makes sense. Okay, but what about this one?
So then what you would have is this carbon would now be overloaded because it would have a double bond here and a double bond here. That's 4. But we have to remember there's an implied hydrogen here. So now it would have 5. So it's breaking the
Yeah.
octet rule. So it's going to kick these electrons onto this carbon. So then there will be a negative charge on that carbon. So it's not that these electrons are jumping all the way to that carbon. It's that they come here and shove those ones out.
Once it comes here, this one goes.
Goes onto this carbon as a negative charge.
So what do we, so, okay, how can we get here?
So there's two ways. Once you have the positive charge here,
Mhm.
you could either get the electrons from here, but this one is also close enough that you could get the electrons from here. So it just depends about which direction you go.
This one.
Mhm.
I'm confused because, oh, it's not there anymore. Okay, yeah. Can I touch it?
Yeah, go ahead.
So yeah, what are we doing right here?
So acidity means that the proton is leaving. The proton leaves and it leaves behind its electrons. So that's how we get from this to this. Now we have a negative charge that we
Okay,
can
so-
do our resonance structures with.
The H is gone,
Yes,
and that's why it's negative.
yes.
Okay, so why are we going this way then? Whoa,
That's the only way we can go
okay.
because there's no other carbon that it can talk to.
Uh-huh.
So it has to go that way. And then it gets trapped because the rule with
and that's why,
resonance,
and that's why we made this one there.
the rule with resonance is you can't break any sigma bonds. So when you have a double bond like this, one of them is a sigma bond and one of them is a pi bond. The pi bonds we can move, the
Mhm.
sigma bonds we cannot. This carbon, it has a sigma bond to this carbon, a sigma bond to this carbon. It also has these two hydrogens that are implied.
Mhm.
So these electrons, they can't come here. This is like a wall where we can no longer move that way because we would have to kick off one of these hydrogens or kick off the carbon, and that would completely change the structure of our molecule.
Mhm.
So that would no longer be a resonance structure. It would be an entirely new compound.
Okay, gotcha. And then-
So the
Yeah,
only
that
place
one.
it can go is down.
Okay, that makes sense. All right, thank you.
What's up?
Well, that mainly answered my questions, but I did want to just double check when labeling the identical atoms, you can number them whatever you want.
Number them however you would like. You could start wherever you would like, as
Just
long
double
as they're the same between the two.
And then for drawing the resonance structures, since you grade everything, do you give partial credit to those that don't like draw all of them? Like say
Yes.
they're missing one?
Yeah.
Thank you.
What's up?
I was gonna ask about, it was number 8, I believe. Oh, no, 9 actually, sorry. Yeah, this one. When you get this structure here,
Mhm.
do you care if I zoom in on it?
Go ahead.
Whenever you move, whenever you move this here,
Mhm.
and then this creates a bond, and this one can't stay. Why is there nothing right here? Because this one would have to move over, right? Or does the
So-
electron just push it here? Like this one moves here, and the electron just goes here. Is that how it is?
So this negative charge
Mhm.
is going to make the bond here,
Right. Yeah. Yeah.
but that's going to make this carbon overloaded. So we have to pick the only pi bond off.
Okay.
I think what you're talking about is like, why can't we move it here?
Yeah. Why doesn't it go here? That's
So
all I'm
it
confused about.
could, but then this one would be overloaded.
Right.
So then we'd have to kick that one. Well, then this one would be overloaded. So then we'd have to kick that one. And
So-
that would just fast track you to
Yeah,
the last one.
Because you're gonna get there anyways.
Yes.
Okay.
And
So-
so that's why we break it down step by step, is because you want to see all of these intermediates and not just the final one.
So then you just put the negative charge because it has too much on the carbon. Okay. And then you mentioned something about nitrogen being chiral in rings.
Mhm.
Is that the case for all of them, or
Not always. You have to make sure that the three things attached are all unique. So
Mhm.
this could be a ring like this.
Yeah.
This would not be chiral because we
Yes.
can draw a line of symmetry down the middle, where these carbons are the same, these carbons are the same, and so it doesn't have
Mhm.
4 unique substituents.
Yeah.
If I added a carbon here, now it is chiral. Because if we folded this like it was a
Mhm.
piece of paper, this would not overlap. So now it's chiral.
Okay.
And then there's the one pair.
Got it. And then you had the lone pair makes it chiral because it has 4 different constituents. Does that go for no, never mind, because nitrogen is the only one that would need one lone
Yes, because oxygen and sulfur will almost always
Two.
have 2.
pair. Right. Okay. Thank you so much.
You're welcome. What's up?
I just want to clarify between
acid, and then conjugate base.
Mhm.
So acid is the one that starts out with like
Proton,
the
or the
proton, and the conjugate base is the one that gains it on the other side of the equation.
Yes.
Okay. Okay. Thank you.
What's up?
Okay. I just needed like, okay, I messed up on the numbering thing. I think it's because I kept on doing like, oops, did not mean to do that. Like 8A for the oxygen, but it's not that. It would be 9.
You can do this, as
Okay,
long
you
as you
can.
do 8A on this one as well.
Okay,
So
I-
here you did it as 9.
Yeah, I
So if
just
you
like
made that
went over the. Okay, so I did that originally on this side. So either way, just as long as they both match up.
Yes.
Okay.
His key shows one right answer. But
Okay.
with these ones, you could start anywhere. You could number it like that, or you could number it like this. They'll
Okay.
all be right.
Okay, I see. And then I had another question about the electron-rich sites.
Mhm.
So how would you? I like assumed it was just where the lone pair and double bonds are originally.
It's not where there's a double bond originally.
Okay.
It is where there's lone pairs originally, but then it's where there's negative charges in the
Okay.
resonance structures.
Okay. So it's just. Okay.
Thank you.
What's up?
For this one, how do you know this is gonna have the extra hydrogen and not like pulling off from here?
It's
Oh,
like with
'cause, like,
buffers.
when I looked it up, it like had an oxygen attached here, so I thought
Yes.
it.
That is a downside of doing the internet-based questions.
Okay, so do I even worry about this for like the exam? Okay, second question was like for the okay. Let me ask you this one. I was like, I don't know
That's
which
okay.
one. For the exam, like knowing the ins and outs of the homework and like practicing examples related to it, that would be the best.
I would say so.
Okay.
And then if there's concepts that you are continuing to struggle with, that is when I would look at external resources.
Okay.
So like if there's any worksheets on the resource guide I have up, that's when you should do those practice problems.
Okay, I've been
If
going through
you are
those,
doing the
so-
homework and you're like, I can't get this down, that's when like you should look elsewhere. But if you can do the homework confidently and like you're like, okay, I got this, it's fine.
So like, yeah, I know like how to do buffers, I know how to do pH, I know how to do like enantiomers and all that. So like, I'm okay.
Yes.
Okay, like some people were like freaking out. I was like, I don't know if I should be freaking out or I shouldn't be freaking out.
I think if you are doing well on the homeworks and you, anywhere that you have mistakes, you can confidently go back and say, okay, I know what I did wrong here.
Yeah.
I know why I did that and why the right answer is what it is. You should be good for the exam.
Okay, sweet. Thank you.
What's up?
Okay, well, so I just had a question. It was about this one. How do you know when to add the H? Is it just like an imaginary like hydrogen gets connected to the? Like, how do you know that was where the acid?
With this question, it's an internet thing.
It is okay. Then I won't worry about this. I was gonna ask on like the problem sets for these. Is it
Mhm.
okay if you number all of them?
Yes,
Okay. Great. I'm probably gonna sit here because I'm gonna. Go
that's okay. What's up?
I don't have a script point, but I just have a question on like the specific. So this
Mhm.
one on the key, it says it's trigonal planar. And I know I put it there, but I
Mhm.
don't actually know why.
Okay, so we'll just draw that part of it. Is there anything implied about this nitrogen that is not drawn?
We'll need lone pairs.
You need one pair. So that's where you get your 3 things. This one also has, this one is kind of a trick question because it does have, not resonance. Yes, resonance.
I don't think
Where-
we've learned resonance yet.
I know he will introduce stuff before you've learned it, just to like get your brain thinking about it. Remember, the homeworks are not graded.
Right.
So it's about like, okay, we've given you the building blocks that you would need to understand this. Can you start thinking about it on your own before it's taught?
Okay.
He won't test like that.
Yeah.
But the homeworks are supposed to get you to start thinking about stuff.
Okay.
So that's why sometimes there are questions on homework that we haven't fully covered.
Okay. So if it has 2 things and the lone pair, then it's trigonal planar. Wouldn't that make it? Then?
That would make that. This is the resonance that I was talking about. So actually.
Oh,
let
so
me
it's
draw
because
it
of
out.
resonance.
Yes. Does that make sense, or do you want me to draw that?
I mean, it makes sense that it's because of resonance, but I don't understand like the resonance.
So. fill this out for you. So we have this lone pair, and we also have the lone pairs on this side. And we can push this. It's also,
That's another thing. Why?
it's in a
can you
ring.
push it? And how do I
That's-
know which one?
Lone pairs, you can push if there's somewhere for them to go.
Just if there's somewhere for them to go.
If
I
there's
can
somewhere
do
for them
that.
to go, they will move.
And so if I can, like, when it asks for resonance structures, if I could find a lone pair that has somewhere to go, I could just start there.
Mhm.
Okay, that makes sense.
So that's the problem with chemistry is a lot of this stuff is constantly moving.
Yeah.
But we can't really draw it out like that. So we have to draw them as like these stagnant images of where the electrons are at a certain time
Okay.
in the universe.
Okay.
But really, like in real life, those electrons are always moving and it's a mix of all of its resonance structures.
Okay. And then also for this one, it's a tetrahedral. Is it also does resonance?
No, so that one has two implied hydrogens.
Oh, I'm just done. Okay, I knew
Don't say that.
No, I knew that. Thank you. That's all.
Mhm. What's up?
Could you explain, it's not on here, can you explain the pH and the buffering thing to me, because I am so confused.
So pKa
Uh-huh,
is going to tell you what your pH buffering range is.
uh-huh.
So usually you'll be given a buffer and he'll tell you what the pKa is, or you'll get a table that includes the pKa. The pH range will be plus or minus 1 of that pH. And so what it means is it is most effective in that range. That is when it can freely give and take take hydrogens or protons. What else do you have questions about in regards to buffers? Like how to identify or, okay, so you'll identify them as an acid and its conjugate base, and they're in a solution together.
Okay,
And then the pKa, based on the functional groups of that molecule, whatever it is, will tell you what pH range it is most qualified to work for. It's kind of hard to explain without an example. So if we look at
it's the other one. Which one is it?
this first question,
Okay.
so he tells you what the base or what the buffer is, which
Mhm.
if this was on an exam, he would give you the structure
Okay.
because obviously you can't look it up. Then you would have your conjugate base and your acid.
Mhm.
And the protonated amine is about where you would get your pKa. This one is a little bit more complicated because there's a lot more periphery
and
going
so-
on.
Once you identify that, that's where you get the pKa
Mhm.
from the chart.
Yes.
Okay.
And so then you can get your pKa or your optimal range, which is about plus or minus what your pKa is. So this would be like 6.4 to 8.4. Well, we actually know the exact numbers for this one because we were able to look it up. But if you're in an exam, you can operate like plus or minus 1 as your assumption. And
So
so
where are we getting this number from?
So if we were on an exam, we could say it was this. But because this was a homework question where it's more about flexing your ability to like use internet resources, we get a more exact number from PubChem or Google if that's what you're using.
What is this number?
So this is the this is the pKa.
Okay. Plus or one, okay,
Mhm.
I got, oh, I get it now, okay. Okay, I get it now. Yeah. Oh, I was like, where's the 8.2 coming from? That's the
That's
range?
the higher range, yeah.
Okay,
So this would be what you would use in an exam when you don't have the exact numbers.
but Google will tell you a more exact range.
Gotcha.
Or your table of buffers, which you won't need for this exam.
I have a question about the range.
Yeah.
On the slides, he said it's 0.5 is the range, and then online it says 1 is the range.
Use one.
Okay. It sort of makes sense, yeah. I also would like, come back to the question, when you like look at that, like, how would you say that? Like molecule peppies?
Keeps.
Keeps, okay. If, when you look at it, how would you know that the nitrogen is the acidic proton?
You would have to see what the conjugate base is.
So would you have to just assume? Because like, since like the sulfur one over to the side doesn't have anything on the list, we would have to like look at the nitrogen within the ring and assume that that is the one that we're gonna be looking at.
If he's giving you a buffer question, he will tell you which proton to focus on.
Okay.
Because with this one, you would have used the internet to find it.
So if it looked like, if it were on the exam, how would he structure the question?
He gives you the acid and the base,
Okay.
or the acid and the conjugate base, and then asks various questions like, using your pKa table, what would the prime pKa of this be? And then what would the optimal pH range with that be?
So he's gonna give us the base, the conjugate base. Okay, so that makes more sense. I thought we just have to infer which one is the acidic.
Not for this exam, maybe when y'all are more advanced,
And like,
but
we could assume or like know that.
when you know more about functionality.
Okay.
Yeah. But for this one, he knows that you are not quite advanced chemists yet.
Basically summarize. So if you get the pKa, you get the range
Mhm.
by subtracting and adding 1.
Mhm.
And then what do you do next?
So then you have the optimal pH. So sometimes you'll get a question that has a bunch of options for molecules, and it's like very basic molecules that would be on your pKa table, and it just says, okay, which I want a solution of pH 10. Which of these would be the best? And so you have to find the pKas of those and see which ones have 10 in that range. So like heaps would not work for a 10. But there are other buffers that have a pH that includes the number 10.
Okay, so if the range was like 8.2 and 9, or like in 10.2,
Yes.
something like that.
Yes.
So you would basically do the same process for each one of those and see which one fall in that range. Okay. It seems like a lot of like work for little time. It's like 6 hours to do the homeworks.
The homeworks are also more questions. So
How many
like this is
parts are
9.
each question? So you said
All in
everything
all, there's like 15 questions.
Okay.
Like if I said 1A, 2A, or 1A, 1B, 1C are each individual questions, there's 15. But
Like would some of them not have any parts to it? Like,
some of them are just one part.
okay. So like you said, question 1 was probably the easiest for like looking at like hydrogens and lone pairs. And then so that one question will probably have like 3 or 4 parts and then so on. So it's gonna be like pretty much the exact same as the homework, just
It's
different
very
questions.
similar to homework.
Would you
That's
say the
why
questions
he
are
tells you.
harder or basically the same, just different words?
He does try to make them a little bit harder because we are trying to like test you on your knowledge. And with your homeworks, you're allowed to use the internet and use your friends and use your resources. So yes, they are a little bit harder. I wouldn't say they're crazy harder. I'd say they're very manageable for what the homeworks are.
Okay, I had a question about number 2, sorry,
Mhm.
video was waiting. So you know how you have found that number and you just plugged it in? Would we be given that number or would we have to find it ourselves?
You would be given that number.
Thank God. Okay, that's all the questions I have.
Or you would be given a periodic table to find it.
Okay.
But for this test, all you have is the pKa table. So if you need it, it would be given to you.
Okay, gotcha.
This is problem set 2.
How do we find like SH is the most acidic acid?
Any proton attached to a heteroatom is going to be pretty acidic.
Okay, so that's why like all of these are just like all hydrogens are the most acidic. But then this one,
Attached to a heteroatom. And this one is not attached to it. It doesn't have any hydrogens.
What's a heteroatom again?
Anything that is not carbon or hydrogen. So nitrogen,
Oh.
sulfur, oxygen, phosphorus.
So like you would look at, for example, this one right here and be like, okay, so there's the weirdo in the group.
Yes.
Okay.
Wait, but
Things
then,
attached to heteroatoms or neighbors of carbocation.
And then so after we would be like, okay, SH, we would go on to the pKa table and
And
look for an SH. Okay.
Wait,
So that makes
a heteroatom
Oh,
is
wait, yeah,
something that's
what about
not
this one?
a carbon or hydrogen?
So nitrogen. So it's either attached to a heteroatom or it's a neighbor to a carbocation.
And the carbocation.
A carbon with a positive charge.
Okay,
Because
so
cations are positive.
yes,
Because
that
of
makes
cat.
sense. So this is the carbocation. And
So
then
all
it
of the
could be-
neighboring,
Okay. And what if like one of these was a nitrogen with an H? Then is that the only one that is gonna be
they would all be acidic and you would have to figure out which one is more acidic.
with, in the one
The
that's?
pKa table.
Okay.
So like this one, you have to figure out which one's more. acidic.
With this one, all three of them are the same amount of acidic because they're all attached to the same nitrogen. Now, if this was a nitrogen, you would have to figure out, okay, what is the pKa for a protonated amine versus what is the pKa for a neighbor of a carbocation? So it would be -3 versus 10.6. So these ones would be more acidic than a
Because it
nitrogen
has a
one.
lower pKa. Okay.
That makes sense.
And then for the conjugate base, should we just rely on the pKa table that shows us the conjugate base? Like that's kind of what I did for like this nitrogen. This is what the
I
conjugate
wouldn't
base looks like.
rely on it
Okay.
because all you're doing is getting rid of a hydrogen
Mhm.
and putting in those electrons.
Okay.
Yeah.
So if like
I
were
guess you can
to-
use it as a resource.
Yeah, that's what I, because
but I
like whenever
would-
I was
I wouldn't
looking at
rely
this, it's basically it looked exactly like this, and then this was the conjugate base, and so I just drew what the conjugate base showed,
Yes.
and I got it right. But
Yes.
would it matter which hydrogen, or does all
No.
that matters is that it's one of the hydrogens?
All those hydrogens are identical, so it does
Okay.
not matter which one you take.
That's what I thought.
The conjugate base is the one that was the acid was.
Yes. Acid minus hydrogen equals conjugate base.
So like relatively, and you're not really like allowed to like speak on, but how many questions would you say are based off of the new content? Like being resonance?
Don't think I can answer that.
Okay.
So I
A
just
good
feel like-
chunk or
I don't think I can answer that.
I'm just trying to just get a mindset of how in depth.
If I had to assume, I would say it's all like equal parts, 1, 2, and 3 of the homeworks, only because that's what it seems like he would do that, but
just because like we just got this homework, but
Yeah.
I know it's not.
resonance is a little new, but I'm not gonna assume that he's only gonna put a little bit of questions on there.
Wait, so for the PKA value placement, is that one just to look up on the internet or had
Yeah.
Okay, so I'm not even aware of that because everything's like look it up. I don't know. Oh, and then so question 2 on the part 3. But you said whenever they don't give you a PKA value, just assume it's a pH and you subtract it from the side.
I don't know where it was, but I think I remember there was a question where it gives you like different pHs. But I don't remember where it was, but it was like a different pH by literally, it's on the slides.
Oh,
There's-
that was a side question.
Yeah, on the slides, it was the only pH problem, but it had a different pH and a pKa, or buffering. Yeah, no, pH and
Okay, and then
pKa.
you subtract. This one's like 0.3 something.
Yes, you subtract, you bring over whatever is with the log, you subtract that from the other side.
Okay.
And then you
Little
take
bit of
the,
algebra.
yeah, and then you take the inverse log, which is 10, and then,
To the
Wait, say that again?
so,
So like this question, it has the pH and the pKa, and they're different. And so you plug those in. And so for this one, you can't just assume that they even out to 0. You have to actually do the math of, okay, I'm gonna subtract 3.8 from both sides, because at the end of the day, we're trying to isolate our x. We're trying to solve for x. So we're doing some algebra. We're subtracting 0.38 from both sides. So you get -0.3 equals log of x over 1. You multiply both sides by 1. So you get log of x equals -0.3. Then you can do 10 to the power and 10 to the power. Yes, yeah. And then to get from 0.5 molar to grams, you would use this.
Gotcha.
and I'm assuming if we are to say there is a problem on the exam with pHs, we're only gonna be needing those two equations, right? The
Those are
negative
the only
log
two
and then that
equations
one.
to know.
Okay, and then I don't know how he could make it harder than this, but like,
No, but there's not really a way.
okay, so it's probably just gonna be.
He could make it like 2 liters or 2 molar, like he could change the values that are here,
Okay,
but it all boils down to this equation.
if he were to change like the liters,
Mhm.
what would change within that equation?
So molarity is the same as moles per liter.
Yes.
So if it were 2 liters, what you're really doing right now is it's 1 liter, so you multiply both sides by 1. So then you get moles, and that's how you can finally go from grams to moles. If it were 2 liters, you would multiply both sides by 2.
To find the mole.
Yes.
Yeah, okay, that would make sense.
Here,
Yeah, so you have to go back to Gen Chem.
Yes, this question relies a lot on your gen chem stuff.
Okay.
That's why the 0.2 by the 0.5.
It would be 2 times 0.5.
Yeah.
oh, okay.
So
Or
you would
moles per
find,
liter. You would divide.
yeah, so you would
So you
find,
multiply both
you
sides.
get the molar and then you would take the liter and then find the moles from that and you'd have to do some crisscrossing.
like a bunch of.
It's algebra
Algebra.
and Gen Chem.
It's gen chem, like algebra stuff, yeah.
So it's only one extra step if he changed. the
Yes.
liters. Is it different with the mole? Or molar?
It would be the same situation.
This, like, acid or base over acid, is that the concentration?
Yes, so the hard parentheses, the brackets, that
Mhm.
means concentration.
Okay, so
Okay.
if
So
like
like the other equation where it's negative log H plus, that one is
the H plus
also
is concentration,
in brackets.
the
And so
ion.
that bracket indicates concentration of whatever's inside the brackets.
okay,
Oh.
so if there were real numbers, then, or if it said like,
You would plug in whatever concentration you get like from the work.
okay,
I know we got lucky on the homework and that concentration was just one or
I'm
point
assuming
one.
it's not gonna be.
Is it, like, is that, when it changes, what would change within the problem?
Well, it depends if you're being given the pH or the concentration of the acid. So if you're given the proton concentration,
You can
which
just
is the
plug it
same
in.
thing as the concentration of the acid, you would plug in for H plus.
Okay,
Whereas if you're given pH, you would plug that in on the other side.
okay, and then would you do the inverse log again? Would it be -10 to the,
So if you were
pH
doing pH, yeah, if you were given pH, you would need to do the inverse log.
okay,
Whereas
would
if
it be
you're given-
-10 or -10? Because there's -10.
-10.
And then also the question was a strong acid, so it dissociates like completely.
Yes.
Is it gonna be like that on the exam too, or, because I don't know how we would solve it with, if it's a weak acid.
If it's a weak acid, you would use the other equation. But for the most part, he will say that.
This one's for strong acids?
Because in Gen Chem, I remember my professor specifically skipped the, if it was a weak acid, how to solve it, because that's
It's-
for like
yeah.
Chem 120.
Yeah.
Okay, so that makes sense then. Do you have any more questions?
Probably, but you know what?
Yeah, I'll realize it at midnight tonight.
So nitric acid is your acid, and this is basically the concentration. So first you have to convert millimoles to molars per millimolar. And that's where you get 100 moles of these. Technically, you're dividing by 1,000, which is how you integrate those on. 1,000 is the unit conversion between moles and moles. If I read it, so this is your concentration of nitric acid. So you plug that in for H plus. Mhm. And then pH. So then you can just plug this into a calculator and it will, or it will spit out.
You write it exactly like that? Okay. Oh, just one. When you go over it in class, right, or like when you go over it, I'm like, oh yeah, like that all makes sense. But when I'm doing the homeworks, I overthink everything and then I don't really get all of it right. But like whenever you talk about it, like, yeah, that makes sense. Like how to go. Oh, I was gonna ask. This is how I did on the homework, but I don't even know. Did I? Do you have to start from the side?
Yes.
Okay. That's right then, and then I only knew that that was like the. So you whenever we do these, you have to draw. On this one, you start from the. Okay, here's what I was confused about while you were going over it. Oh, just like the movement of like the negatives. So with electrons, the arrows are always pointing to negative. So when you're dealing with the negative will go point. Whereas when you're dealing with positive, it will always seem to push to the arrow because you're leaving a vacancy there. So the positive has a minus push to the arrow, or it has a positive has a minus push. So like based on these, is it going from so it's going like this one to this one, and then this, or is it skipping just one? So these two electrons from nitrogen are making a pi bond between the nitrogen and the carbon. That causes this carbon to be overkilled. They have more than an octet than it's allowed. So there's two carbons here, or there's two bonds here, then there would be two bonds here, plus the implied hydrogen. You can't break these bonds because that is not a resonance structure. Resonance structure has the same molecular compound, just a little bit different. And so you would have to push this pi bond off. So you could push it like this to make another pi bond, but then you run into the same problem because now it's carbon. So then you would have to push it again. And if you just kept doing that, you would end up at the last structure. So instead, you stop at all of the intermediates and put the negative so that you can see all of the different stops in between those two. That's why you don't put another double bond there.
Yes.
Okay, I was like, because I knew that there was gonna be one there, but I just didn't add it because we weren't adding it. So this right here, just saying that this is gonna be overflowed with this one.
It's saying that in order to avoid overflow, it's just going to hold on to the lone pair.
So this one. You start with the.
So you're trying to fill that void of electrons.
Oh, so you go to the one that's next to it.
Mhm.
That goes in the next double one.
And then you created a new void.
Okay. I think I understand. Okay. I think that's it. I'm gonna. Do you think it'd be okay if I just like redid all the homeworks again?
Yes, so